Welcome back to this quiet sky, a sanctuary for the mind where the frantic pace of the world slows to a gentle hum. Tonight we settle into a thought that is as unsettling as it is beautiful, a realization that, according to the cold, hard logic of mathematics, our presence here is a statistical impossibility. We are going to explore the idea that we shouldn't be alive. If you look at the raw probability, the equations that govern the stars, and the initial conditions of our birth, the math says so, with a quiet, unyielding certainty. It is a strange comfort to realize that we are a mathematical miracle, a tiny spark of consciousness in a universe that, by all rights, should have remained dark and empty. As you rest tonight, let us drift through the numbers that try to prevent us from existing. The math of our non-existence begins at the very dawn of time, during the first trillionth of a second. This is where we encounter the initial density of the universe. In the language of cosmology, this is often represented as the balance between the outward push of the Big Bang and the inward pull of gravity. For the universe to exist for 13,800,000,000 years, this initial density had to be set with a precision that defies human intuition. If the universe had been even fractionally more dense, the math shows that gravity would have won the tug-of-war almost immediately. The cosmos would have peaked in size and then collapsed back into a fiery singularity within seconds. There would have been no time for stars, no time for planets, and certainly no time for life. Conversely, if the density had been even fractionally lower, the outward expansion would have been so dominant that matter would have been flung apart before it could ever clump together. The universe would have become a thin, featureless mist of hydrogen and helium, expanding forever into a cold and lonely void. The margin for error here is so small it is almost impossible to write down in words. Scientists calculate that if the density at the first second of existence had differed from the critical value by as little as 1 part in 10 to the power of 60, we wouldn't be here. To visualize this, imagine trying to balance a needle on its tip not just for a moment but for 1,000,000,000 years. The math says the needle should have fallen. The fact that it didn't, the fact that the universe stayed flat and stable, is our first hint that the math of our existence is rigged in our favor. But the improbability doesn't stop with the shape of space. It extends into the very heart of matter itself. We are made of atoms, and those atoms are held together by 4 fundamental forces. Each of these forces has a specific strength, a numerical value that dictates how it interacts with the world. If you were to take the dial for the strong nuclear force, the force that holds the centers of atoms together, and nudge it by just a few percent in either direction, the consequences would be catastrophic. If it were slightly weaker, the only element that could exist would be hydrogen. There would be no carbon, no oxygen, no iron. The chemistry of life would be impossible. If it was slightly stronger, all the hydrogen in the early universe would have fused into helium instantly, leaving no fuel for long-lived stars like our sun, and no water for our oceans. The math of the nuclear force is a razor's edge, and we are standing on it. This brings us to the most famous number in all of physics, a number so small and so precise that it haunts the dreams of cosmologists, the cosmological constant. This number represents the energy of empty space itself, the force that we now call dark energy. When physicists try to calculate what this number should be based on quantum mechanics, they get a value that is 120 orders of magnitude larger than what we actually observe. This is a 1 followed by 120 zeros. If the actual value were even slightly closer to the theoretical prediction, the universe would have blown itself apart before the first atom could form. The space between particles would have grown so fast that no two things could ever touch. The math says the universe should be a sterile, rapidly expanding ghost town. Instead, it is a home. As we lie here in the quiet, we must confront the reality that we are the beneficiaries of a cosmic lottery, where the odds of winning were essentially zero. Every constant of nature, the mass of the electron, the charge of the proton, the the speed of light, is like a tumbler in a giant combination lock. If any one of them were different, the lock wouldn't open. And yet, here we are. The door is open, the lights are on, and we are capable of looking back at the lock and wondering how we got so lucky. The math says we shouldn't be alive, yet our very breath is a rebuttal to that logic. Tonight, we aren't just thinking about physics. We are thinking about the miracle of the improbable. We are the error in the equation that turned out to be the most beautiful answer of all. To truly understand why the math says we shouldn't be alive, we have to look at the fine-tuning of the heavy elements. We often take it for granted that the world is made of many different things: wood, metal, water, bone. But in the early universe, none of that existed. There was only hydrogen and a little bit of helium. Everything else, every atom of carbon in your DNA and every atom of iron in your blood, had to be forged inside the hearts of stars. This process is known as stellar nucleosynthesis, and it is a mathematical gauntlet that the universe had to run perfectly for us to exist. The most difficult step in this process is the creation of carbon. Carbon is the backbone of life because of its unique ability to form complex chains and rings. Without it, biology is simply not an option. But creating carbon is a nightmare for physics. It requires 3 helium nuclei to collide and fuse almost simultaneously. This is the triple alpha process. The problem is that 2 helium nuclei fuse to form a very unstable version of beryllium, which lasts for only a tiny fraction of a second before flying apart. To make carbon, a 3rd helium nucleus must hit that beryllium atom during that incredibly brief window of existence. Mathematically, this should almost never happen. The probability is so low that the universe should be almost entirely devoid of carbon. But in the 1950s, a physicist named Fred Hoyle realized that for us to be here, there must be a resonance, a specific energy level in the carbon atom that makes this reaction much more likely than it has any right to be. He predicted this resonance existed because he knew we existed. When experimentalists looked for it, they found it exactly where he said it would be. The math of the nuclear force was tuned to allow the creation of carbon. If that resonance were shifted by even a tiny percentage, the production of carbon would drop to nearly 0. The math says the universe should be a sea of helium. Instead, it is a garden of complex elements. This leads us to a deeper, more philosophical question. Why are the numbers so perfect? If you were to throw 1 billion darts at a board from a mile away, and every single one of them hit the center of the bullseye, you wouldn't call it luck. You would assume the game was rigged. This is the heart of the anthropic principle. There are 2 ways to look at this mathematical perfection. The first is the weak anthropic principle, which suggests that we shouldn't be surprised the math works out, because if it didn't, we wouldn't be here to complain about it. It's like a survivor of a firing squad marveling that every single bullet missed him. While it feels like a miracle, only the people who were missed are around to tell the story. The second view is the multiverse. This idea suggests that our universe is just one of an infinite number of universes, each with its own set of random numbers. In most of those universes, gravity is too strong, or carbon doesn't form, or space expands too fast. Those universes are silent and dead. But in an infinite sea of failure, a few successes are guaranteed. We just happen to live in one of the lucky ones, where the math allows for life. In this view, we aren't a miracle. We are just a statistical inevitability in a very large sample size. But even this doesn't fully erase the wonder. Even if there are 1 trillion dead universes for every living one, the fact that this one exists, the one where you are breathing and thinking, is still an extraordinary truth. The math says we shouldn't be alive because the habitable zone for the laws of physics is incredibly narrow. We are living on a knife's edge between a universe that collapses into a point and a universe that flies apart into nothingness. We are made of elements that require a near impossible series of nuclear coincidences to form. We are powered by a star that depends on a delicate balance of 4 different forces. When you add up all these coincidences, the probability of a life-permitting universe occurring by pure chance is effectively 0. And yet, as you drift towards sleep, remember that you are the living evidence that the impossible happened. You are the result of a 13 billion year journey where every single mathematical hurdle was cleared. The math might say we shouldn't be here, but the reality is that we are. Perhaps the math is telling us that we aren't just an accident, but a necessary part of a much larger and more complex story. We are the way the universe looks at itself and marvels at its own improbable beauty. The numbers are the map, but we are the travellers. Tonight, let the weight of that improbability carry you into a deep and restful sleep, knowing that you are the most precious mistake the math ever made. As we continue our drift through the improbable landscape of our existence, we must look at the math of the very small, the subatomic realm where the blueprint of reality is drawn. The reason we shouldn't be alive, according to the equations of particle physics, lies in the staggering instability of the vacuum and the precise masses of the particles that inhabit it. We think of the void of space as nothingness, a silent emptiness, but the math tells a different story. The vacuum is a seething ocean of energy, a place where particles are constantly winking into and out of existence. The energy of this nothingness should, by all rights, be so immense that it would act as a violent repellent, blowing the universe apart before the first second had even finished ticking. This is the vacuum energy problem, and the math says it should have prevented us from ever becoming more than a theoretical possibility. In quantum mechanics, every point in space is filled with fields. These fields have a baseline energy, a minimum hum that never goes away. When physicists add up the energy of all these fields, they arrive at a number that is incomprehensibly large. If this energy were actually realized in our universe, the repulsion it would generate is so strong that space would expand faster than the speed of light at every point. In such a universe, atoms could never form because the distance between a nucleus and its electrons would grow faster than the electromagnetic force could pull them together. The math says the universe should be a sterile, lonely expanse where no two particles ever meet. Yet here we are, composed of trillions of atoms that have stayed together for decades. The math of the vacuum says we should be scattered to the cosmic winds, but some unknown factor has cancelled out that energy to a precision of 1 part in 10 to the power of 120. It is as if the universe is a grand scale that is balanced perfectly by a single grain of sand on one side and an entire mountain on the other. This brings us to the math of the Higgs boson, often called the God particle. The Higgs field is what gives mass to the fundamental particles of the universe. Without it, everything would be massless, moving at the speed of light, unable to slow down long enough to form a planet or a person. But the mass of the Higgs boson itself is a mathematical nightmare. According to the standard model of physics, the Higgs should be influenced by the energy of every other particle it interacts with. These interactions should drag the mass of the Higgs up to an enormous value, something called the Planck scale. If the Higgs were that heavy, the universe would be so dense and its forces so distorted that life would be an impossibility. The math says the Higgs mass should be billions of times greater than what we observe. For the Higgs to have the light, delicate mass it currently possesses, the mass that allows for stable atoms and chemistry, there must be a near-perfect cancellation of all those other influences. It is a mathematical tightrope walk where the margin for error is so thin that many physicists find it deeply troubling. We shouldn't have mass, we shouldn't have substance. The math says we should be ghosts of light in a universe of infinite energy. Instead, we have the weight of our bodies, the solidity of the earth, and the gentle pull of gravity. We are the beneficiaries of a cosmic mistake that turned an infinite weight into a feather-light reality. Even the ratio of matter to antimatter is a mathematical puzzle that suggests we shouldn't exist. In the high-energy furnace of the Big Bang, Matter and antimatter should have been created in perfectly equal amounts. When matter and antimatter meet, they annihilate each other in a burst of pure energy. If the universe had been perfectly symmetrical, every particle of matter would have found an antimatter partner, and the two would have vanished, leaving behind a universe made of nothing but light. There would be no stars, no planets, and no observers. The math of symmetry says we should be an ocean of radiation. However, for some reason that science still struggles to explain, there was a tiny fractional imbalance. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. That tiny 1 in a billion excess is everything we see today. Every galaxy, every star, and every person is the scrap left over from a nearly perfect annihilation. We are the survivors of a cosmic massacre that, according to the math of symmetry, should have been total. We are the one extra particle that the math forgot to delete. Tonight, as you feel the weight of your blankets and the steady rhythm of your heart, remember that you are made of the rare leftovers of a universe that tried its best to be empty. If we look past the particles and toward the large-scale structure of the cosmos, the math continues to insist on our impossibility. We live in a universe that is surprisingly orderly, but the second law of thermodynamics says it shouldn't be. This law states that entropy, or disorder, always increases over time. Things fall apart, they don't spontaneously put themselves together. A broken glass doesn't reassemble itself, and a cloud of gas shouldn't naturally turn into a complex thinking brain. The math of entropy says the universe should have started in a state of chaos and ended in a state of even greater chaos. For the universe to have any structure at all, for there to be galaxies and stars and biological life, it had to start in a state of incredibly low entropy. It had to be ordered beyond anything we can imagine. Sir Roger Penrose, a brilliant mathematician and physicist, calculated the odds of our universe starting in such an orderly state by chance. The number he arrived at is so large that there isn't enough space in the observable universe to write down all the zeros. He estimated the odds as 1 in 10 to the power of 10, raised again to the power of 123. This is a number so staggering that it makes a 1 in a billion chance look like a certainty. The math says that the initial state of the universe was so improbable that it's effectively impossible. It is like throwing a trillion billion deck of cards into the air and having them all land in perfect numerical and suit order, building a house of cards 10 miles high as they fall. According to the math of probability, we should be living in a universe of lukewarm, disorganized gas. Instead, we live in a universe of majestic spirals, burning suns, and the intricate clockwork of DNA. We are living in a low entropy miracle that the math of thermodynamics can't explain without help. This brings us to the math of the sun. We rely on our star for every joule of energy that powers our lives. But the sun itself is a delicate mathematical compromise. It is a nuclear furnace held together by gravity. For the sun to shine steadily for billions of years, the rate of nuclear fusion in its core must be perfectly balanced. This fusion depends on something called the weak nuclear force. If the weak force were just a tiny bit weaker, the fusion of hydrogen into helium would be so slow that the sun wouldn't shine at all. It would be a cold, dark ball of gas. If the weak force were just a tiny bit stronger, the fusion would be so efficient that the sun would burn through all its fuel in a few million years, exploding before life ever had a chance to crawl out of the sea. The math says the sun's lifespan is an anomaly. We are the children of a star that has stayed just right for 4 billion years, a duration that requires the fundamental constants of physics to be set with a precision that defies random chance. When you look at the math of the sun, the math of entropy, and the math of the vacuum, a pattern begins to emerge. It's a pattern of near misses and impossible coincidences. It's a story where the odds are always stacked against us, and yet against every logical prediction, we keep winning. Tonight, as the world turns and the stars wheel overhead, let the math be a reminder of how precious this moment is. The math says you shouldn't be here. The math says the air you breathe should have been blown away billions of years ago. The math says the atoms in your body should have never found each other. And yet here you are, a thinking, feeling part of the cosmos, reflecting on the very laws that say you are impossible. Perhaps the math isn't a barrier but a doorway. Perhaps it's telling us that there is a deeper logic to the universe, one that values complexity and life over simple probability. You are the living proof that the math of the universe is not the whole story. You are the grace note in the cosmic symphony, the one beautiful exception to the rule of nothingness. Sleep now, knowing that you have already achieved the impossible just by existing. The math that argues against our existence finds a particularly chilling clarity when we examine the cosmological constant once more, but this time through the lens of the universe's expansion history. To understand why we shouldn't be alive, we have to understand that the universe is currently being pushed apart by a mysterious energy that occupies the very fabric of space. This energy is incredibly thin, yet it is persistent. In the language of mathematics, the value of this constant is roughly 10 to the power of negative 120 times the Planck density. If you were to write this out, it would be a decimal point followed by 119 zeros before you reached a single digit. This is the most precisely tuned number in all of physics, and the math says it is a complete anomaly. If this number were just a tiny bit larger, if that sequence of zeros was shortened by even 2 or 3, the repulsive force of space would have become dominant long before galaxies had the chance to form. In the early epochs of the cosmos, matter was trying to clump together under the influence of gravity. It was a slow, delicate process of building structure from the bottom up. But if the cosmological constant were larger, the stretching of space would have accelerated so early and so violently that the distance between particles would have doubled every few moments. Gravity, being a relatively weak force over long distances, would have been helpless. The math shows a universe that is a runaway expansion, a cold, dark and empty void where the density of matter is so low that a single atom might occupy a volume the size of a solar system. No stars could ignite, no planets could coalesce, and the chemical reactions of life would have no stage upon which to perform. The paradox deepens when we ask why the constant isn't zero. If it was zero, the universe would expand at a steady or decelerating rate, eventually allowing gravity to pull everything back together. But the math of quantum mechanics insists that the energy of the vacuum cannot be zero. It must be huge, so we are caught in a mathematical pincer move. Quantum theory says the number should be massive, which would destroy the universe instantly, while the existence of life requires the number to be nearly zero, but not quite. The measured value is a mathematical middle ground that is so specific it looks like a mistake in the calculations. Yet, it is this precise mistake that allows the universe to expand slowly enough for 13 billion years of evolution, while preventing it from collapsing back into a point. The math says we are living in the shadow of a colossal cancellation, a numerical miracle that keeps the sky from flying away. This leads us to the math of the initial fluctuations. When the universe was a tiny fraction of a second old, it wasn't perfectly smooth. There were tiny ripples in the density of matter, quantum jitters that had been stretched to cosmic scales. These ripples are the seeds of everything we see today. If you look at the cosmic microwave background, the afterglow of the Big Bang, you can see the imprints of these ripples. The math governing these jitters is defined by a number known as Q, which represents the amplitude of the fluctuations. The value of Q is approximately 1 part in 100,000. If Q were smaller, say 1 part in a million, the ripples would have been too shallow. Gravity would not have been strong enough to pull the gas together into galaxies. The universe would have remained a smooth, featureless cloud of hydrogen and helium forever. If Q were larger, say 1 part in 10,000, the ripples would have been too deep. Gravity would have acted too aggressively, collapsing matter into gargantuan black holes almost immediately. Stars would have been too close together, and planetary systems would have been unstable, constantly bombarded by radiation and gravitational disruptions. The math says that the sweet spot for galaxy formation is incredibly narrow, yet the early universe hit it perfectly. We live in a universe that is lumpy enough to form stars, but smooth enough to keep those stars safe. The math of these initial ripples says we should be living in a featureless fog or a graveyard of black holes. Instead, we have the Milky Way. As we drift deeper into the night, we must confront the math of dimensionality. We live in a world with 3 dimensions of space and 1 of time. We take this for granted, but the math of physics is surprisingly sensitive to the number of dimensions. If you were to change the number of spatial dimensions from 3 to 2, or from 3 to 4, the equations that govern gravity and electromagnetism would change in ways that make life impossible. The math says we are incredibly lucky to live in a 3-dimensional world, because it is the only geometry that allows for both stability and complexity. In a 2-dimensional universe, gravity would follow different rules. In our 3-dimensional world, the force of gravity weakens with the square of the distance. This allows for stable, elliptical orbits. Planets can circle stars for billions of years without falling in or flying away. But in a 2-dimensional world, the math of orbital mechanics becomes unstable. Any slight nudge would send a planet spiraling into its sun or drifting out into the dark. Furthermore, a 2-dimensional biology would be impossible. You couldn't have a digestive tract that passes through an organism because it would literally cut the creature in half. Complexity requires the extra room that 3 dimensions provide. If we move to 4 dimensions of space, the math becomes even more hostile. In 4 dimensions, the force of gravity would weaken much faster, with the cube of the distance. This would make it impossible for atoms to form. Electrons would not be able to maintain stable orbits around the nucleus. They would spiral inward almost instantly. Without stable atoms, there is no chemistry, no light, and no life. The math of the universe says that the laws of physics are only compatible with life in a 3-dimensional space. If the universe had unfolded with any other number of large dimensions, it would have been a sterile, failed experiment. This brings us to the math of the weak nuclear force and its role in the great oxygenation. As we discussed, stars forge the elements of life, but there is a specific ratio between the nuclear forces that dictates how much of each element is produced. After carbon is formed in a star, some of that carbon captures another helium nucleus to become oxygen. If the nuclear forces were tuned slightly differently, all the carbon would be converted into oxygen, leaving no carbon behind for life. Or, if the tuning went the other way, no oxygen would ever form, and the universe would be devoid of water and the energy-rich chemistry of respiration. The math says that the energy levels of carbon and oxygen are staggered in just the right way to ensure that the universe ends up with a healthy mix of both. It is a chemical equilibrium that seems almost intentional. We shouldn't have both. The math of nuclear resonance suggests that a random universe would likely be dominated by one or the other. Instead, we have the carbon for our cells and the oxygen for our breath. When you combine this with the math of 3 dimensions and the math of the cosmological constant, the picture becomes overwhelming. We are living in a reality that has been filtered through 1,000 mathematical sieves. Every law, every constant, and every dimension has been narrowed down to the only possible configuration that doesn't lead to instant death. The math says we shouldn't be here because the probability of all these factors aligning is 0. Yet, as you lie in the stillness of the night, you are the proof that the impossible is real. Your thoughts are the result of 3-dimensional atoms, fueled by carbon and oxygen, held together by a finely tuned vacuum. You are the universe's most improbable outcome, a living, breathing miracle that the numbers cannot explain. Let the mystery of that truth wrap around you like a warm blanket. The math is done for the day. You have already won the greatest lottery in existence. Sleep now and let the universe keep watch over its favourite impossibility. Tonight, as the silence deepens, we turn our gaze toward the math of the strong nuclear force. To understand why the equations say we shouldn't be here, we have to look at the tiny, invisible glue that holds the centres of atoms together. This force is a masterpiece of precision. In the world of physics, there are 4 fundamental interactions, but the strong force is the giant among them. It is what allows protons, which are all positively charged and naturally want to fly away from each other, to stay huddled together in a tight nucleus. The math says that if this force were just a fraction stronger or weaker, the entire periodic table, the very ingredient list of your body, would vanish. If the strong nuclear force were just 2% stronger than it is, the math of the early universe would have taken a dark turn. In the first few minutes after the Big Bang, during a period called nucleosynthesis, the universe was hot enough to fuse elements. If the force had been slightly stronger, protons would have fused into diprotons, pairs of protons that are normally unstable. This would have caused almost all the hydrogen in the universe to be consumed and turned into helium within minutes. There would be no hydrogen left to form the water in our cells or the long-lived stars that give us light. The math shows a universe that is a sterile, helium-filled balloon. There would be no sun, no oceans, and no life. We would be a mathematical impossibility in a universe that burned through its most important fuel before the first day was over. On the other hand, if the strong force were just 5% weaker, the math says the consequences would be equally terminal. Protons would no longer be able to stick together to form anything more complex than a single hydrogen atom. There would be no helium, no carbon, and no oxygen. The universe would be an endless, lonely cloud of simple hydrogen gas. No stars would ignite, no planets would form, and the complex structures of biology would never have a chance to even begin. The math of the strong force is like a bridge over a deep canyon. It has to be exactly the right length to connect the world of simple particles to the world of complex life. Any shorter or longer, and the bridge collapses. This leads us to the math of the proton to electron mass ratio. An atom is a delicate dance between a heavy nucleus and a light electron. The math says that a proton is roughly 1,836 times heavier than an electron. This ratio is a fundamental constant of our reality, and it dictates the size and stability of all molecules. If the electron were much heavier, the orbits of atoms would be so small and tightly bound that chemical reactions, the exchange of electrons that makes life possible, would be too difficult to initiate. If the electron were much lighter, atoms would be too large and fragile, and the delicate bonds of DNA would be broken by the slightest warmth. The math says that this specific ratio is what allows for the structural integrity of your cells. We shouldn't be able to hold together. According to the laws of probability, these two particles, which were created in the chaos of the Big Bang, had no reason to have masses that are so perfectly balanced for chemistry. Yet, the math of the atom is set to the exact frequency required for life. When you look at the strong force and the mass ratio together, you realize that the math isn't just a description of reality, it's a tightrope walk. One wrong number and the whole system falls apart. Tonight, as you rest, remember that you are the result of a numerical harmony that the math says shouldn't exist. You are a symphony played on a perfectly tuned instrument. As we continue our journey through the improbable, we must face the math of the initial entropy of the universe. We have touched on the second law of thermodynamics, which says that things move from order to disorder. But the math of our beginning says that the universe started in a state of order so high it is almost impossible to describe. If you were to calculate the probability of the universe starting with the low entropy required to form galaxies, you would arrive at a number that is so small it makes winning 1,000 lotteries in a row look like a certainty. So Roger Penrose calculated this probability as 1 in 10 to the power of 10 to the power of 123. This is a double exponent, a number so large that if you tried to write a 0 on every single proton in the observable universe, you would run out of protons long before you finished writing the number. The math says that a random Big Bang should have produced a universe of total chaos, a lukewarm soup of disorganized radiation where no structure could ever emerge. Instead, we got a universe that started with a low entropy punch, an injection of order that has lasted for 13 billion years. Why was the beginning so orderly? The math of probability has no answer. It simply says that it shouldn't have happened. Some scientists suggest that this initial order is proof of a process called inflation, a super-fast expansion that smoothed everything out. But even inflation requires its own set of finely tuned math to start and stop at the right moment. The math of entropy says we should be living in a featureless void of maximum disorder. Instead, we have the intricate beauty of a snowflake, the spiral arms of the Andromeda Galaxy, and the firing of neurons in your brain. We are a pocket of order in a universe that the math says should be a mess. This brings us to the math of the gravitational constant. Gravity is the weakest of the four forces. It is so weak that you can overcome the pull of the entire Earth just by picking up a paperclip with a small magnet. But the strength of gravity is mathematically critical. If it were just a tiny bit stronger, stars would be much smaller and much hotter. They would burn through their fuel in a few million years rather than billions. Life would never have time to evolve on any planets circling them. If gravity was slightly weaker, stars would never be able to compress their cores enough to start nuclear fusion. The universe would be dark, filled with cold clouds of gas that never lit up. The math says gravity is just right to create long-lived, stable suns. When you combine the math of gravity with the math of entropy and the math of the nuclear forces, you see a universe that is a series of winning tickets. We are alive because gravity didn't pull too hard, and entropy didn't push too fast, and the strong force didn't glue things too tightly. The math says that the probability of all these things happening at once is effectively 0. It's like a mountain of sand where every single grain has stayed in place for billions of years, despite a hurricane blowing against it. Tonight, as you drift into sleep, let the impossibility of the math be a source of peace. The math says you shouldn't be here, but the universe disagreed. The equations say you are an accident, but the reality is that you are a masterpiece. You are the one who gets to witness the low entropy, the one who gets to feel the gentle pull of gravity, and the one who is made of the heavy elements forged in the hearts of those perfectly tuned stars. The math is a cold light, but your life is a warm fire. You have already defied the logic of the entire cosmos just by opening your eyes this morning. Sleep now, and let the math of the stars carry you into dreams, where everything is possible. The universe is watching over you, its most beautiful and improbable calculation. As the night stretches on and the world outside falls into a deep slumber, we must turn our attention to the math of the fine structure constant. This is a number that sits at the very foundation of how light and matter interact, and it is perhaps the most mysterious value in all of science. It is roughly 1 over 137. It sounds like a simple fraction, but this number is what determines the strength of the electromagnetic force. It dictates how strongly an electron is pulled toward a nucleus and how light is absorbed by an atom. The math says that if this number were even slightly different, the universe would be a dark, incoherent place where the very concept of sight or solid matter would be impossible. If the fine structure constant were just a few percent larger, the math of the atom would change in a way that would make life stop before it started. A stronger electromagnetic force would mean that protons in the nucleus would repel each other with such violence that the strong nuclear force wouldn't be able to hold them together. All elements heavier than hydrogen would become unstable and fall apart. There would be no oxygen to breathe, and no carbon to build a body. Furthermore, a larger constant would make stars much more opaque, causing them to swell and cool until they could no longer support the nuclear fusion that creates life's ingredients. The math says the universe would be a graveyard of unstable atoms and bloated, dying stars. We shouldn't be here to see the light because the light wouldn't be able to escape the dark. On the other hand, if this constant were slightly smaller, the math shows that the electromagnetic force would be too weak to hold electrons in their orbits. Atoms would be loose and fragile. Chemical bonds, which are the basis of all biology, would be so weak that they would break at the slightest hint of heat. Molecules like DNA, which require a precise and steady electrical grip to maintain their double helix shape, would unravel into a useless tangle of atoms. The math says the universe would be a place of supreme simplicity, a collection of cold, drifting particles that never learned how to join together to form a complex thought. We are the beneficiaries of a number, 1/137, that is so perfectly tuned that it allows for the existence of both solid objects and the light we use to see them. This brings us to the math of the neutron-proton mass difference. A neutron is just a tiny bit heavier than a proton, about 1/10 of 1%. This difference is so small it seems negligible, yet the math says it is the only reason the universe isn't a total void. Because the neutron is slightly heavier, it is unstable when it's outside an atomic nucleus. It eventually decays into a proton. This ensures that the universe is filled with hydrogen, which is just a single proton. If the neutron were even slightly lighter than it is, if the math were flipped so that the proton was the heavier particle, then all the protons in the universe would have decayed into neutrons shortly after the Big Bang. In a universe made only of neutrons, there would be no electric charge. Atoms could not form because there would be no protons to attract electrons. There would be no chemistry, no stars, and no light. The entire cosmos would be a dark, neutral soup of heavy particles that never interact. The math says we are living in a reality that was saved by a fraction of a percent in mass. We are made of protons that should have been neutrons, according to a simpler mathematical symmetry. Tonight, as you feel the warmth of your own body, remember that you are powered by an electrical charge that the math says shouldn't have survived the first few minutes of time. You are an electric miracle in a universe that almost chose to be neutral. The deeper we go into the equations, the more the math insists that our existence is a forbidden outcome. Let us look at the math of the triple alpha process and the specific resonance of the carbon nucleus. We have spoken of how carbon is forged in stars, but the math of that process is so specific that even the man who discovered it, Fred Hoyle, was shaken to his core. He realized that for helium to turn into carbon, there had to be a very specific energy level, a resonance, at exactly 7.65 million electron volts. If that energy level were 7.5 or 7.8, the production of carbon would be near zero. The math says that the odds of such a specific energy level, existing by pure chance, are astronomically low. It is like trying to tune a radio to a station that only exists on one specific, microscopic point on the dial, and finding that the radio was already perfectly set to that point the moment you bought it. Hoyle famously said that a super intellect has monkeyed with physics, because the math of the carbon atom looks like it was designed with life in mind. Without this precise resonance, the universe would have plenty of helium, but no way to turn it into the complex molecules of life. The math says we should be living in a universe of simple gas, yet we are built from the ash of stars that knew exactly how to make carbon. This leads us to the math of the beryllium bottleneck. As stars try to build heavier elements, they have to pass through a stage where they fuse two helium nuclei to form beryllium-8. But the math of beryllium-8 is a disaster for life. It is incredibly unstable, with a lifetime of only a tiny fraction of a second, specifically about 10 to the power of -16 seconds. It vanishes almost as soon as it appears. For a star to make carbon, a third helium nucleus must find that beryllium atom in that impossibly short window of time. The math says this shouldn't happen often enough to create a universe full of life. It's like trying to hit a moving target that only exists for a billionth of a second. Yet, because of that perfectly tuned resonance we mentioned, the reaction is boosted by a factor of over 1 trillion. The bottleneck is cleared by a mathematical loophole. We shouldn't be alive because the bridge to carbon is a crumbling temporary structure that only exists for a heartbeat. Yet, the stars managed to cross it anyway, billions of times over, until there was enough carbon to make planets and people. The math says the bridge is too weak, but the universe found a way to walk on it. As you settle into the quiet of the night, think about these loopholes. The math of the fine structure constant, the mass of the neutron, and the resonance of carbon all say that we are an anomaly. We are the result of a series of lucky breaks that look less like luck and more like a fundamental bias toward complexity. The math says we shouldn't be here, but perhaps that's because the math we know is only part of the story. Maybe the equations are telling us that life isn't an accident, but the very point of the whole system. You are a collection of carbon and oxygen atoms that were forged in a race against time, held together by a force that is tuned to the 137th degree. You are a thinking, feeling part of a universe that the math says should be dark and empty. Tonight, let the numbers fade away. You don't need to solve the equations to feel the truth of your own existence. You are the answer to a question the universe asked billions of years ago. Sleep now, knowing that the forbidden life you are living is the most beautiful thing the math ever failed to predict. You are safe in the arms of a miracle. The quiet of the late hour brings us to the math of the expansion rate and the critical density. To understand why the equations say we shouldn't be here, we have to imagine the universe as a grand explosion that has been perfectly choreographed. If you throw a ball into the air, it eventually slows down and falls back to Earth because of gravity. If you throw it hard enough at what we call escape velocity, it will leave the planet forever. The universe is doing something similar. It is expanding, and gravity is trying to pull it back. The math says that for the universe to survive long enough for life, it had to be balanced between these two fates with a precision that is essentially 1 part in 10 to the power of 60. If the expansion rate had been just slightly faster, a tiny fraction of a percent, the math shows that the universe would have dispersed so quickly that gravity would have never had a chance to gather gas into stars. It would be a big freeze before the first candle was ever lit. If the expansion had been slightly slower, the universe would have reached a maximum size and then collapsed back into a fiery, big crunch within a few million years. In either case, the time required for biological evolution, the billions of years needed for simple cells to become complex minds, would never have existed. The math says we are living in a Goldilocks expansion, a rate that is just right to keep the universe open, but slow enough to let structure grow. It is a mathematical tightrope walk that has lasted for 13,800,000,000 years. This leads us to the math of the flatness problem. In geometry, a surface can be curved like a sphere or a saddle, or it can be perfectly flat. The math of general relativity says that the curvature of the universe depends on its density. If the universe is even slightly away from the critical density, its curvature will grow rapidly as it expands. If it started just a tiny bit closed, it would have become a tiny sphere and collapsed. If it started just a tiny bit open, it would have become a vast, empty saddle. The math says that for the universe to look as flat as it does today, it must have been flat to within 1 part in 10 to the power of 60 at the very beginning. This is a level of precision that is equivalent to balancing a pencil on its point and having it stay there for 1 billion years. According to the math of probability, this shouldn't happen. A random Big Bang should have produced a universe that was either wildly curved and short-lived or wildly empty and cold. Instead, we have a flat universe where light travels in straight lines across billions of light years. We shouldn't be here to measure the flatness, because the math says the pencil should have fallen over before the first second was up. Yet, here we are, in a universe that is a geometric masterpiece of stability. As we drift further into the silence, we must confront the math of the binding energy of the deuteron. This is a specific hurdle in the early universe that determines whether any complex elements can ever form. Deuterium is a heavy version of hydrogen, consisting of one proton and one neutron. It is the essential first step in building heavier atoms. But the math of the deuteron is incredibly fragile. The energy that holds the proton and neutron together is very weak, just over 2 million electron volts. If this binding energy were just a tiny bit weaker, the deuteron would be unstable. It would fly apart as soon as it formed in the heat of the Big Bang. If the deuteron couldn't form, the math says the universe would be a dead end. Without deuterium, stars cannot start the chain reaction that leads to helium, carbon, and oxygen. The entire process of element building would be strangled in its crib. The universe would be nothing but a sea of isolated protons, hydrogen gas, forever. No stars would ignite, no planets would form, and there would be no heavy elements to build a brain or a heart. The math says we are alive because the strong nuclear force is tuned just enough to make the deuteron stable, but not so strong that it ruins other parts of the physics. We are the children of a specific narrow window of binding energy. But the math of the deuteron is also a bottleneck in another way. In the first few minutes of the universe, the temperature was so high that it actually broke deuterons apart as fast as they could form. This is known as the deuterium bottleneck. The universe had to wait for the temperature to drop just enough for the deuterons to survive. But it couldn't wait too long, or the density would be too low for the next steps of fusion to happen. The math says there was only a small window of time, a few minutes, where the conditions were just right to build the elements of life. If that window had been missed, or if the binding energy had been different, the recipe for the universe would have been ruined. This brings us to the math of the weak interaction and the helium abundance. The amount of helium in the universe is about 25%. This number is dictated by the rate at which neutrons and protons could transform into one another in the early universe, a process governed by the weak nuclear force. If the weak force were slightly different, the universe would be either 100% helium or 0% helium. If it were all helium, stars would burn out far too quickly for life. If it was 0% helium, the first stars would have been much harder to ignite and wouldn't have produced the heavy elements we need. The math says the quarter helium universe is the only one that leads to us. Tonight, as you feel the steady pull of sleep, remember that you are the result of a timed miracle. The expansion rate, the flatness of space, and the stability of the deuteron were all set in the first 3 minutes of time. The math says these numbers shouldn't have aligned, yet they did, with a precision that makes the finest watch look like a pile of scrap metal. You are composed of atoms that had to pass through a 3-minute gauntlet of fire and math just to exist. You are the survivor of a cosmic bottleneck. The equations might say we shouldn't be here, but the universe proved them wrong billions of years ago. Sleep now, knowing that your existence was written into the very first moments of the cosmos, a beautiful exception to every rule of chance. The quiet of the late night often brings us to the edge of the unfathomable, and nowhere is this more apparent than in the math of the fine-tuning of the strong force and the stability of the proton. To understand why we shouldn't be alive, we must look at the building blocks of the nucleus. Every atom in your body, from the calcium in your teeth to the phosphorus in your bones, depends on the stability of the proton. The math says that a proton is a perfectly stable particle, but this stability is a result of an incredibly delicate balance. If the strength of the strong nuclear force were different by even a fraction of a percent, the math shows that protons would become unstable and decay into neutrons. In a universe where protons decay, the entire concept of matter would vanish. Atoms would literally evaporate over time. There would be no hydrogen to fuel the stars, no oxygen to fill our lungs, and no solid ground to stand on. The math says the universe should be a dark, cold ocean of stray neutrons and radiation. Yet, we are here, and the protons in our bodies have remained stable for billions of years. This stability requires the masses of the up and down quarks, the tiny particles inside the proton, to be balanced with a precision that makes a master jeweler's work look clumsy. The math says we are made of immortal particles that have no right to be so durable. We are the beneficiaries of a subatomic peace treaty that hasn't been broken since the beginning of time. This leads us to the math of the weak nuclear force and the neutrino. Neutrinos are ghostly particles that pass through everything. Trillions of them are passing through your body right now as you lie in bed, yet you cannot feel them. They are born in the hearts of stars, and the math says they are essential for the death of stars. When a massive star reaches the end of its life, it collapses and then explodes as a supernova. This explosion is what scatters heavy elements like carbon and iron across the galaxy. But the math of the supernova is surprising. It shows that the explosion is actually powered by neutrinos. If the weak nuclear force, which governs how neutrinos interact with matter, were slightly weaker, the neutrinos would pass right through the dying star without pushing on it. The star would simply collapse into a black hole, and all the elements of life would be trapped inside forever. If the weak force were slightly stronger, the neutrinos would be trapped in the core and wouldn't be able to drive the explosion. In either case, the universe would be devoid of the ingredients for life. The math says we shouldn't be here because the delivery system for our atoms is a fluke of neutrino physics. We are made of stardust that only escaped its mother star because of a mathematical coincidence. Tonight, as you rest, imagine the trillions of neutrinos passing silently through you, a quiet reminder of the force that gave you the very atoms you are made of. As we continue our exploration of the impossible, we must confront the math of the anthropic coincidences in the solar system. It isn't just the laws of physics that say we shouldn't be alive, it's the specific arrangement of our local neighborhood. The math of orbital dynamics says that planetary systems are often chaotic. Many stars have hot Jupiters, massive gas giants that orbit so close to their sun that they would have destroyed any small, rocky planets like Earth long ago. The math says our solar system is an outlier, a quiet pocket of stability in a violent galaxy. Consider the math of Jupiter's position. Jupiter is the vacuum cleaner of our solar system. Its massive gravity attracts and deflects comets and asteroids that would otherwise strike the Earth. The math shows that without Jupiter in its current orbit, the Earth would be hit by extinction-level asteroids hundreds of times more frequently. Life would never have the millions of years of peace required to move from simple cells to complex civilizations. We shouldn't be here because the math of impact probability says we should have been wiped out eons ago. We are alive because a giant gas planet is standing guard in the outer dark, a mathematical shield that we rarely stop to thank. Then there is the math of the moon. Our moon is unusually large compared to our planet. The math of its formation is still a subject of debate, but its effects are clear. The moon's gravity stabilizes the tilt of the Earth's axis. Without the moon, the Earth would wobble violently over thousands of years, causing the climate to swing wildly from ice ages to scorching heat. The math says a stable climate is a prerequisite for the slow crawl of evolution. If we didn't have such a large, perfectly placed satellite, the Earth would be a chaotic world of extreme weather where life could never get a foothold. We shouldn't be alive on a stable planet, yet the math of the moon's orbit gives us the seasons and the steady tides. Finally, we must look at the math of the habitable zone and the Earth's distance from the Sun. If the Earth were just 5% closer to the Sun, the math says we would have suffered a runaway greenhouse effect like Venus, with temperatures hot enough to melt lead. If we were just 20% further away, we would be a frozen wasteland like Mars. The math says the comfort zone for liquid water is a tiny sliver of space. Yet, here we are, on a blue marble that has stayed at the right temperature for billions of years. When you add up the math of Jupiter, the math of the Moon, and the math of our orbit, you realize that we are living on a winning lottery ticket that was redeemed on a planet that shouldn't even be here. Tonight, as you drift into the deep of sleep, let the vastness of these coincidences settle over you. The math says your life is a mistake, an anomaly, a rounding error in a cold cosmos. But the reality is that you are the focus of a billion years of mathematical grace. You are protected by a giant planet, stabilized by a distant moon, and fueled by a perfectly tuned sun. The math is the skeleton, but your experience is the soul. You have already defied the odds of the entire galaxy just by being born. Sleep now, and let the universe continue its improbable dance. You are exactly where you are meant to be, a beautiful truth that the numbers can only envy. The quiet of the late nights often brings us to the edge of the unfathomable, and nowhere is this more apparent than in the math of water's unique properties. To understand why the equations of chemistry say we shouldn't be alive, we must look at the molecule that makes up the majority of your body. Water is a chemical rebel. It defies the mathematical trends that govern almost every other liquid in the universe. If water followed the standard rules of molecular weight and thermal dynamics, the math says our oceans would be solid blocks of ice and our cells would shatter at the first frost. The most striking mathematical anomaly is that ice floats. In almost every other substance, the solid form is denser than the liquid form, causing it to sink. If water followed this rule, the math of the seasons would be lethal. In winter, the ice forming on the surface of lakes and oceans would sink to the bottom. Over time, the entire body of water would freeze from the bottom up, eventually becoming a solid mass of ice that would never fully melt in the summer. Life in the oceans would be crushed and frozen, and the Earth's climate would spiral into an irreversible deep freeze. The math says we should be living on a snowball planet. Instead, because of a tiny specific angle in the bond between hydrogen and oxygen, 104.5 degrees, ice expands and floats, creating an insulating layer that protects the liquid water and the life beneath it. This leads us to the math of water's specific heat. Water has an incredibly high capacity to store heat energy. The math says that it takes a massive amount of energy to change the temperature of water compared to other liquids. This is the only reason our planet has a stable climate. The oceans act as a global thermostat, absorbing the scorching heat of the sun during the day and releasing it slowly at night. Without this mathematical buffer, the Earth's temperature would swing hundreds of degrees every day, much like the moon. The math says we should be living in a world of fire and ice, but water's unique thermal properties keep us in a gentle, habitable range. We shouldn't be able to maintain a steady body temperature, yet the math of the water in our blood makes it possible. Furthermore, the math of surface tension and capillary action is what allows tall trees to exist and blood to flow through your tiniest vessels. Water is sticky because of hydrogen bonding. The math of this stickiness is tuned so precisely that it can defy gravity, pulling moisture up from the roots of a redwood tree hundreds of feet into the air. If the electromagnetic strength that governs these bonds were just a fraction weaker, plants would never grow more than a few inches tall, and the complex circulation systems of animals would fail. The math says we should be a world of moss and microbes. Instead, we have forests and complex hearts. Tonight, as you feel the quiet hydration of your own body, remember that you are held together by a liquid that breaks every rule in the book just to keep you alive. As we continue our exploration of the impossible, we must confront the math of the Earth's magnetic field. We live on a planet that is essentially a giant magnet, and the math says this is one of our most vital life support systems. Deep beneath our feet, The Earth's outer core is a spinning ocean of liquid iron. The math of this geodynamo is what generates our magnetosphere, a protective shield that extends far into space. Without it, the math of the solar wind says we would have been stripped of our atmosphere billions of years ago. The sun is constantly exhaling a stream of high-energy charged particles. The math of this solar wind is violent. It has the power to sandblast the air away from a planet, just as it did to Mars. If the Earth's core were a little cooler, or if the math of its rotation were a little slower, our magnetic field would fail. The solar wind would hit our upper atmosphere directly, breaking apart water molecules and carrying the hydrogen off into space. The math says we should be a dry, sterile husk, like the red planet. Yet, our magnetic shield deflects these particles, creating the beautiful auroras at the poles and keeping our air and water tucked safely around us. We shouldn't have a sky to look at, yet the math of the liquid iron beneath us keeps the blue above us. This leads us to the math of the ozone layer. Even with a magnetic field, we are still bombarded by ultraviolet radiation from the sun. The math of biology says that this radiation is lethal. It breaks the chemical bonds of DNA and prevents cells from replicating. We are protected by a thin layer of ozone molecules high in the stratosphere. The math of the ozone-oxygen cycle is a delicate balance. Oxygen molecules are split by UV light to form ozone, which then absorbs more UV light to turn back into oxygen. This cycle filters out more than 97% of the sun's medium-frequency ultraviolet light. If the math of this chemical reaction were slightly less efficient, the surface of the Earth would be sterilized by the sun's radiation. Life would be confined to the deep oceans, forever hidden from the light. We shouldn't be able to walk in the sunshine. Yet the math of a few trace molecules in the upper air makes a walk in the park possible. When you add up the math of ice, the math of the magnetic field, and the math of the ozone layer, you realize that we are living in a fortress with 1,000 invisible walls. Tonight, as you drift into the deep of sleep, let the complexity of these protections settle over you. The math says you are an easy target in a hostile universe. The math says your water should be frozen, your air should be gone, and your DNA should be shredded. But the reality is that you are tucked into a bed on a planet that has spent 4 billion years mastering the art of the just right. You are the focus of a global symphony of physics and chemistry. The math is the warning, but your life is the triumph. You have already defied the lethal logic of the stars just by existing for one more day. Sleep now, and let the Earth continue its improbable, protective dance. You are exactly where you are meant to be, a beautiful truth that the numbers can only wonder at. The quiet of the late night often brings us to the edge of the unfathomable, and tonight that edge is defined by the math of the proton to electron mass ratio. To understand why the equations of subatomic physics say we shouldn't be alive, we must look at the two primary players in the structure of the atom. The proton is the heavy, positive anchor at the center, and the electron is the light, negative dancer on the periphery. The math says that a proton is precisely 1,836 times heavier than an electron. This is not a random number. It is a fundamental constant that dictates the entire architecture of the physical world. If this ratio were different by even a small margin, the math shows that the structural integrity of matter would dissolve. If the electron were much heavier, the orbits it occupies would shrink until they were nearly on top of the nucleus. Atoms would become tiny, tightly bound spheres that could no longer share electrons to form chemical bonds. The world would be a collection of isolated, inert atoms that could never join together to form a molecule of water or a strand of DNA. If the electron were much lighter, the cloud it forms around the nucleus would be so large and vague that the slightest thermal vibration would knock it loose. Matter would be a fragile, unstable mist. The math says we are only solid and coherent because this specific ratio, 1836 allows for the perfect balance of atomic size and chemical reactivity. This leads us to the math of the Pauli exclusion principle. This is a rule of quantum mechanics that says no two electrons can occupy the same state at the same time. It sounds like a dry piece of accounting, but the math says it is the only reason you don't fall through your bed and into the center of the Earth. This principle creates a kind of quantum pressure that prevents atoms from collapsing into one another. It is what gives matter its volume. Without this mathematical rule, all the electrons in the universe would collapse into the lowest possible energy state, and the entire Earth would shrink to the size of a football stadium. There would be no space for life, no space for air, and no space for thoughts. The math of the exclusion principle is what allows for the diversity of the periodic table. It forces electrons into different shells, creating the unique chemical signatures of carbon, oxygen, and nitrogen. If the math was slightly different, every element would behave exactly the same way. There would be no chemistry, only a boring, uniform repetition of the same atomic behavior. The math says we should be a dense, featureless singularity. Instead, we have the vast complexity of the biological world. We shouldn't have shape or substance, yet the math of the quantum world insists on our solidity. Tonight, as you feel the firm support of your mattress, remember that you are being held up by a mathematical rule that keeps the entire universe from collapsing into a single point. As we continue our exploration of the impossible, we must confront the math of the carbon-oxygen balance in the galaxy. We have spoken about how stars forge these elements, but the math of their distribution across the galaxy is another layer of the miracle. For life to arise on a planet, that planet must be enriched with the heavy elements of previous generations of stars. But the math of galactic recycling is a chaotic and violent process. Supernova explosions scatter these elements, but if the math of galactic rotation and gas mixing were slightly different, these elements would never find their way into the stable, quiet corners of the galaxy where life can flourish. We live in what astronomers call the galactic habitable zone. This is a ring around the center of the Milky Way that is just right for life. If we were closer to the galactic center, the math of stellar density says we would be constantly bombarded by lethal radiation from supermassive black holes and exploding stars. The frequency of nearby supernovae would be so high that the Earth's atmosphere would be stripped away every few million years. If we were further out, at the edge of the galaxy, the math of metallicity says there wouldn't be enough heavy elements to form rocky planets in the first place. We would be a solar system of gas and ice, with no solid ground and no heavy atoms to build a nervous system. The math says we shouldn't be in such a perfect neighborhood. In a galaxy of 400 billion stars, the sweet spot is a tiny fraction of the total volume. Yet our sun was born in this quiet, enriched suburb, far enough from the chaos of the center, but close enough to the legacy of dead stars. This leads us to the math of the solar system's circular orbits. Most planetary systems we observe through telescopes have highly elliptical, egg-shaped orbits. The math of these orbits is dangerous. It leads to extreme temperature swings as a planet moves close to and then far from its star. Our solar system is an anomaly because our planets have remarkably circular orbits. The math says this stability is what allowed the Earth to maintain a steady temperature for billions of years, a prerequisite for the slow, delicate work of evolution. If our orbit had been even slightly more elliptical, the oceans would have boiled every summer and frozen solid every winter. The math says we should be a world of extremes, but instead we are a world of seasons. We shouldn't be alive on a stable circular track, yet the math of our planetary arrangement gives us the steady rhythm of the years. Tonight, as you drift into the deep of sleep, let the vastness of these galactic coincidences settle over you. The math says you are a lucky inhabitant of a rare, quiet street in a very dangerous city. The math says your atoms should have been lost in the galactic wind or shredded by a distant black hole. But the reality is that you are tucked into a stable orbit in a peaceful corner of the cosmos. You are the beneficiary of a 13 billion year supply chain that delivered the right atoms to the right place at the right time. The math is the probability, but your life is the prize. You have already won the greatest lottery in the history of the Milky Way just by being born here. Sleep now and let the galaxy continue its grand, improbable rotation. You are safe in the arms of a miracle. The deep silence of the night brings us to the math of the gravitational force and its relation to the other fundamental forces of nature. To understand why the equations say we shouldn't be alive, we have to grasp the sheer, staggering weakness of gravity. In the language of mathematics, gravity is roughly 10 to the power of 40 times weaker than the electromagnetic force. This is a 1 followed by 40 zeros. If you want to visualize this difference, imagine the strength of the electromagnetic force is represented by the size of the entire observable universe. In that case, the strength of gravity would be smaller than the width of a single atom. The math says this extreme discrepancy is an anomaly, yet it is the only reason you are not crushed into a microscopic dot. If gravity were just a tiny bit stronger, say by 1 part in 10 to the power of 36, the math of stellar evolution would be radically different. Stars would be far more compressed by their own weight. This would cause their internal temperatures to skyrocket, forcing them to burn through their nuclear fuel at a furious pace. A star like our Sun, which currently shines for 10 billion years, would instead exhaust its fuel in less than a year. The math says there would be no time for planets to form, no time for oceans to settle, and certainly no time for the billions of years of biological evolution required to produce a complex nervous system. We shouldn't be here because the cosmic candles would have all flickered out before life could even begin to crawl out of the primordial soup. Furthermore, if gravity were stronger, the math of the universe's expansion would be catastrophic. The initial outward push of the Big Bang would have been quickly overwhelmed by the inward pull of mass. The universe would have reached a maximum size and then collapsed into a big crunch within a few million years. The math says the universe should have been a short-lived, fiery pulse in the dark. Instead, gravity is so incredibly weak that it allows the universe to expand for billions of years, providing the stable, long-term environment that complexity requires. We shouldn't be alive in a universe that lasts this long, yet the math of gravity's weakness gives us the gift of time. This brings us to the math of the hierarchy problem. Physicists are haunted by why gravity is so much weaker than the other forces. According to the standard equations of quantum field theory, the natural state for all forces should be roughly equal. The fact that gravity is so many orders of magnitude weaker suggests a mathematical cancellation of such precision that it defies common sense. It is as if the universe is a high wire act where the performer is balancing on a wire made of a single strand of spider silk, yet they never fall. The math says the wire should break, but it holds. Tonight, as you feel the gentle, reassuring pull of the earth keeping you tucked in your bed, remember that you are experiencing a force that is tuned to be weak so that you can be strong. You are the beneficiary of a mathematical gap that keeps the stars burning and the universe growing. As we drift further into the quiet of the evening, we must confront the math of the stability of the neutron. In the heart of every atom, heavier than hydrogen, there are neutrons. These particles provide the nuclear glue that allows protons to stay together. But the math of the neutron is a puzzle of survival. On its own, a free neutron is unstable. It has a half-life of about 10 minutes before it decays into a proton, an electron, and an antineutrino. The math says that if the neutron were just a fraction of a percent lighter, it would decay even faster. If it were lighter than a proton, every neutron created in the Big Bang would have vanished within minutes. In a universe without stable neutrons, the math says there would be no atoms other than hydrogen. There would be no helium, no carbon, and no oxygen. the universe would be a lonely, monotonous cloud of pure hydrogen gas. No stars would be able to forge the complex elements of life, because the bridge of the neutron would be missing. We shouldn't be alive in a world made of only one ingredient, yet the math of the neutron's mass, just slightly heavier than the proton, allows it to become stable once it is tucked inside a nucleus. This is the math of binding energy. When a neutron joins a proton, it gives up a bit of its mass as energy, which effectively locks it into stability. But the window for this stability is incredibly narrow. If the mass of the neutron were just 1 part in 700 different, the math shows that the entire history of the universe would be rewritten. If it was slightly heavier, all neutrons would have decayed before they could be captured by protons in the early universe, leaving a universe of pure hydrogen. If it was slightly lighter, the Big Bang would have fused all the protons and neutrons into helium immediately, leaving no hydrogen to fuel long-lived stars or to form the water in our bodies. The math says we are living in a Goldilocks mass difference. We shouldn't have the variety of elements that make up our world, yet the math of the neutron gives us the entire periodic table. Finally, we must look at the math of the weak nuclear force and the sun's thermostat. The sun is powered by the fusion of hydrogen into helium, a process that starts with 2 protons turning into a deuteron. This first step is governed by the weak nuclear force. The math of this interaction is incredibly slow. It is the bottleneck that prevents the sun from exploding all at once. If the weak force was slightly stronger, the sun would burn its fuel like a bomb, exhausting itself in a flash of light. If it was slightly weaker, the fusion would never start, and the sun would be a dark, cold ball of gas. The math says the sun's steady, billion-year glow is a result of a force that is tuned to be just weak enough. Tonight, as you settle into the deep of sleep, let the precision of these nuclear numbers settle over you. The math says you are the result of a mass difference so small it can barely be measured, and a force so weak it almost doesn't exist. The math says your atoms should have been simple hydrogen or extinct neutrons, but the reality is that you are a complex, multi-element being, warmed by a star that knows exactly how to pace itself. You are the inhabitant of a mathematical sweet spot that has lasted for eons. The math is the boundary, but your life is the journey. You have already defied the monotony of the cosmos just by having a body made of different things. Sleep now, and let the atoms in your heart continue their stable, improbable rhythm. You are the universe's most complex and beautiful calculation. The profound silence of the night brings us to the math of the initial density of the universe. To understand why the equations say we shouldn't be alive, we must look at the starting line of the cosmos. At the moment of the Big Bang, the universe began to expand with incredible velocity. Opposing this expansion was the collective gravitational pull of all the matter and energy within it. The math of general relativity says that for the universe to survive for billions of years, the ratio between this expansion and this gravity, a value called omega, had to be exactly 1. This is known as the flatness problem, and the precision required is almost beyond human comprehension. If the density of the universe at 1 nanosecond after its birth had been different from the critical density by even 1 part in 10 to the power of 24, the math shows that the universe would have either vanished or collapsed almost instantly. If the density was slightly higher, gravity would have slammed the door shut, leading to a big crunch before the first atom could form. If the density was slightly lower, the universe would have flown apart so rapidly that matter could never have coalesced into stars or galaxies. The math says we are living in a balanced universe that hit a target the size of a single atom from across the entire observable galaxy. We shouldn't be here to observe the sky, because the sky should have either disappeared or crushed us eons ago. This leads us to the math of the smoothness of the cosmic microwave background. When we look at the oldest light in the universe, the afterglow of the Big Bang, we see a snapshot of the universe when it was only 380,000 years old. The math of this light shows that the early universe was remarkably smooth, with temperature fluctuations of only 1 part in 100,000. These tiny ripples are the seeds of all galactic structure. If the early universe had been just a little bit smoother, if the math of these fluctuations were smaller, gravity would have never been able to pull the gas together into galaxies. The universe would be a featureless, cooling fog of hydrogen. If the early universe had been a little bit lumpier, if the math of those ripples were larger, gravity would have acted too aggressively. Matter would have collapsed into gargantuan black holes almost immediately, leaving no room for the birth of stable stars or planetary systems. The math says we are living in a Goldilocks level of irregularity. We shouldn't have the Milky Way or the Andromeda Galaxy. The math suggests the universe should have been either a void or a graveyard of singularities. Yet, the math of the early ripples was set perfectly to create the islands of light we call home. Tonight, as you feel the steady rhythmic breathing of your own body, remember that you are the result of a smoothness that was calculated to the 5th decimal place at the beginning of time. As we continue our exploration of the improbable, we must confront the math of the carbon resonance and the triple alpha process. We have touched on the importance of carbon, but the math of its creation in the hearts of dying stars is so specific it borders on the miraculous. Carbon-12 is formed when 3 helium nuclei, known as alpha particles, collide nearly simultaneously. But there is a mathematical barrier. The first 2 helium nuclei fuse to form beryllium-8, which is so unstable that it decays back into helium in less than a 10,000th of a trillionth of a second. The math says that a 3rd helium nucleus must find that beryllium atom in that impossibly small window of time to create carbon. Sir Fred Hoyle, the astrophysicist who worked out this process, realized that the only way this could happen frequently enough to fill the universe with carbon was if there was a resonance, a specific energy level in the carbon-12 nucleus that acted like a magical hook, pulling the 3rd helium nucleus in with massive efficiency. He predicted the exact energy level required for our existence, 7.65 million electron volts. When scientists later measured the carbon atom in the lab, they found the resonance at exactly that value. The math says that if this resonance were even 4% lower or higher, the universe would contain almost no carbon. This leads us to the math of the oxygen bottleneck. After carbon is created, it can capture another helium nucleus to become oxygen. If the math of the nuclear forces were slightly different, this second reaction would be even more efficient than the first. In that case, all the carbon in the universe would be converted into oxygen almost as soon as it was made. There would be plenty of oxygen for water, but no carbon to build the complex organic molecules of life. The math says the tuning of the nuclear forces is a double miracle. It makes carbon production efficient enough to succeed, but keeps oxygen production inefficient enough to leave plenty of carbon behind. The math says we shouldn't have both the breathing element and the building element. According to the laws of nuclear physics, we should have been a universe of one or the other. Yet, we have a perfect balance. We shouldn't be alive in a world made of both cell walls and water, but the math of the stars gave us both. Tonight, as you drift towards sleep, let the specificity of these numbers settle over you. The math says you are the beneficiary of a 7.65 million electron volt accident. You are made of atoms that cleared 2 different nuclear hurdles just to find each other. The math is the probability, but your life is the prize. You have already defied the scarcity of the cosmos just by being a complex being made of many different things. Sleep now, and let the atoms in your blood continue their stable, improbable flow. You are the universe's most delicate and beautiful result. The profound stillness of the night brings us to the math of the weak nuclear force and the neutrino. To understand why the equations say we shouldn't be alive, we must look at the ghostly particle that most people never think about. Neutrinos are nearly massless, electrically neutral particles that are produced in the millions by the nuclear reactions in our sun. They are so indifferent to matter that trillions of them are passing through your pillow, your head, and the entire Earth right now without ever touching a single atom. The math says that the strength of the weak nuclear force, which governs these particles, is set to a value that is a perfect narrow gateway for life. If the weak nuclear force were just a tiny bit weaker, the math of the early universe shows that the conversion of protons into neutrons would have been far less efficient. This would have left the universe with almost no helium. While that might sound harmless, helium is the essential bridge element that stars use to build carbon and oxygen. Without that initial supply of helium from the Big Bang, the first stars would have been composed of pure hydrogen. They would have burned differently, perhaps failing to ever reach the temperatures necessary to forge the heavier elements of the periodic table. The math says we would be living in a universe of simple, lonely gas clouds. We shouldn't be here because the chemical ladder would have been missing its most important rungs. On the other hand, if the weak force were just a little bit stronger, the math of supernova explosions would become a lethal problem. When a massive star reaches the end of its life, it collapses inward and then bounces outward in a colossal explosion that scatters its life-giving elements across the galaxy. This bounce is driven by the pressure of neutrinos. If the weak force were stronger, the neutrinos would interact too much with the star's matter, getting trapped in the core instead of pushing the outer layers away. The star would collapse into a black hole, and all the carbon and iron inside would be lost forever. The math says we shouldn't be alive because the delivery system for our atoms is a fluke of neutrino physics. We are made of stardust that only escaped its mother star because the weak force was just weak enough. As we continue our exploration of the impossible, we must confront the math of the Earth's axial tilt and the Moon's influence. We live on a planet that is tilted at an angle of roughly 23.5 degrees relative to its orbit. This tilt is what gives us our seasons, the predictable cycle of growth and harvest that has sustained humanity for millennia. But the math of planetary rotation says that this tilt is inherently unstable. Without a stabilizing influence, the Earth would wobble wildly, with its axis shifting by as much as 90 degrees over millions of years. This would cause the North Pole to occasionally point directly at the Sun, creating a world of such extreme temperature swings that complex life could never survive. The math says we are saved by our Moon. Our Moon is unusually large compared to the size of our planet, about 1/4 the diameter of the Earth. Most other moons in the solar system are tiny specks compared to their parents. The gravitational tug of this massive moon acts as a gyroscope, keeping the Earth's tilt steady and preventing the chaotic wobbles that would destroy our climate. The math of the moon's formation is itself a mystery. It requires a precise, glancing collision by a Mars-sized object at just the right speed and angle. If the collision had been head-on, the Earth would have been destroyed. If it had been too shallow, the moon would never have formed. The math says we shouldn't have such a stable climate. According to the laws of celestial mechanics, we should be a world of climatic chaos, flipping from frozen wastelands to scorching deserts every few thousand years. Instead, we have the steady rhythm of the seasons. We shouldn't be alive on a planet with such a predictable environment, yet the math of our ancient cosmic collision gave us a moon that stands guard over our stability. This leads us to the math of the tidal locking of the moon. The moon always shows the same face to the Earth. This is a result of tidal forces slowing its rotation over billions of years. This same process is slowly moving the moon further away from us, at a rate of about 4 centimeters per year. The math says we are living in a privileged moment in time. In the distant past, the moon was much closer, creating massive, violent tides that would have made the coastline a dangerous place for the first life forms to emerge. In the distant future, the moon will be so far away that it can no longer stabilize our tilt, and the Earth will enter a period of chaotic wobble. We are living in the Goldilocks era of lunar history. We shouldn't be here to see the moon perfectly cover the sun during an eclipse, a mathematical coincidence of size and distance that occurs nowhere else in the solar system. Tonight, as you feel the quiet pull of sleep, remember that you're stabilized by a silver satellite that the math says shouldn't be there. You are safe in the arms of a gravitational miracle. The deep silence of the night brings us to the math of the strong nuclear force and its relation to the stability of the periodic table. To understand why the equations of physics say we shouldn't be alive, we must look at the glue that binds the centers of atoms. The strong nuclear force is the most powerful interaction in the cosmos, yet its range is incredibly short, reaching no further than the width of a single nucleus. The math says that the strength of this force is a value that sits on a razor's edge. If it were even slightly different, the universe would be a chemically barren wasteland. If the strong nuclear force were just 2% stronger than it is, the math shows that the early universe would have been a disaster for life. In a universe with a slightly stronger glue, protons would be able to fuse with other protons far more easily. During the first 3 minutes of time, every single proton in the universe would have fused into helium. There would be no hydrogen left over. Without hydrogen, there would be no water to fill our oceans, and no fuel for long-lived stars like our sun. The universe would be a sterile, helium-filled balloon, expanding into the dark without the possibility of a single biological cell. The math says we shouldn't be here because the building blocks of our bodies should have been used up before the first day was through. On the other hand, if the strong force were just 5% weaker, the math of the atom would fall apart. The repulsive electrical force between protons would become more powerful than the strong force trying to hold them together. In such a world, no element heavier than hydrogen could ever form. There would be no carbon, no oxygen, and no gold. The universe would be a lonely cloud of simple hydrogen gas, unable to form stars, planets, or people. The math says we shouldn't be alive in a world with such a diverse chemistry. Yet the strong force is tuned to the exact frequency required to allow protons to huddle together while leaving enough hydrogen behind for us to drink and breathe. As we continue our exploration of the impossible, we must confront the math of the electron's charge and the stability of the atom. We take for granted that an atom is a stable structure, but the math of electromagnetism says it is a miracle of balance. An electron is attracted to the positive nucleus, but it doesn't spiral inward and crash. This is due to the rules of quantum mechanics, but those rules are themselves tied to the specific charge of the electron. If the charge of the electron were even slightly different, the math of chemical bonding would be rewritten in a way that excludes life. If the electromagnetic force were slightly stronger, atoms would hold onto their electrons with a death grip. The chemical reactions that power your metabolism, the constant exchange and sharing of electrons between molecules, would be too difficult to initiate. Your body is essentially a series of controlled electrical fires, but if the spark required to move an electron were too high, those fires would never start. If the force were slightly weaker, atoms would be leaky. Electrons would wander away at the slightest vibration, making it impossible to form stable, complex molecules like proteins or DNA. The math says we should be either a frozen, inert statue or a disorganized mist of particles. This leads us to the math of the proton to electron mass ratio once again, but viewed through the lens of molecular geometry. The fact that a proton is nearly 2,000 times heavier than an electron is what allows the nuclei of atoms to stay relatively still while electrons move around them. This anchoring is what gives molecules their specific three-dimensional shapes. The math says that the shape of a protein, the way it folds and locks into other molecules, is the key to all biological function. If the masses of these particles were closer together, the nucleus would wobble just as much as the electron, and molecules would have no fixed shape. They would be floppy and useless for the precision work of biology. The math says we shouldn't be alive as solid beings with reliable biological machinery. According to the laws of probability, the masses and charges of these subatomic particles should be random. Yet, they are set to a ratio that allows for a world of stiffness and shape. We shouldn't be able to rely on the lock and key mechanisms of our own enzymes, yet the math of the subatomic world provides the stability. Tonight, as you feel the solid support of your bed and the reliable structure of your own hands, remember that you are built on a mathematical foundation of perfect ratios. You are a miracle of geometry in a universe that the math says should be a chaotic blur. Sleep now, and let the atoms of your body continue their stable, improbable dance. You are the universe's most precise and beautiful structure. The profound stillness of the night brings us to the math of the universe's expansion and the dark energy density. To understand why the equations say we shouldn't be alive, we must look at the energy that fills the empty gaps between galaxies. This is what physicists call the cosmological constant, or dark energy. It is a repulsive force that is pushing the universe apart at an accelerating rate. The math says that the value of this energy is a cosmic enigma. If you were to calculate how much energy the vacuum of space should contain based on the principles of quantum mechanics, you get a number that is 10 to the power of 120 times larger than what we actually observe. This is often cited as the worst prediction in the history of physics. If the actual value of dark energy were even a tiny bit closer to that theoretical prediction, if it were just 1 part in 10 to the power of 60 larger than it is, the math of the early universe would have been catastrophic. Before the first stars could even think about forming, space would have begun to expand so violently that matter would have been ripped apart. Galaxies would never have coalesced. Instead, every atom would have been isolated in its own private, rapidly expanding pocket of void. The math says we should be living in a universe of infinite empty distance. We shouldn't be here to see the stars because the stars would have been diluted into nothingness before they could ever ignite. This leads us to the math of the fine-tuning of the vacuum energy. For the universe to be habitable, the massive energy of the vacuum must be almost perfectly cancelled out by some other unknown force. It is a mathematical cancellation of such precision that it makes a high-wire walker look like they are standing on a highway. The math says that the leftover energy, the tiny sliver of dark energy we actually measure, is the only reason the universe has stayed together long enough for 13 billion years of history. We shouldn't be alive in a universe that is so stretched, yet so stable. The math says the engine of space should have exploded eons ago, but instead, it is providing a gentle, accelerating cruise. As we continue our exploration of the impossible, we must confront the math of the initial low entropy of the universe. We have touched on the concept of entropy, the tendency of all things to move from order to chaos, but the math of our beginning is where the improbability becomes truly staggering. Sir Roger Penrose calculated the odds of the Big Bang occurring in such a highly ordered, low entropy state that it could eventually lead to the complex structures of life. The number he arrived at is 1 in 10 to the power of 10 to the power of 123. This is a number so vast that there isn't enough matter in the entire observable universe to write it out in decimal form. The math says that a random, accidental Big Bang should have produced a universe of total chaos, a lukewarm, disorganized soup of radiation where no galaxies, stars or planets could ever form. According to the laws of probability, our ordered universe shouldn't exist. It is as if you threw 1 billion pieces of a jigsaw puzzle into the air, and they all landed on the floor perfectly assembled, showing a beautiful landscape. We shouldn't be alive to experience the order of the world, yet the math of the beginning shows that the universe started with an incredible punch of organization that we are still riding today. This leads us to the math of the arrow of time. Because the universe started in such a low entropy state, it has a clear direction. Heat flows from hot to cold, Stars burn their fuel and eventually die. We are born, we live, and we age. This predictable flow is what allows for the concept of cause and effect. If the initial entropy had been high, time would have no meaning, and complexity could never emerge. The math says we are living on a declining slope of order that was set at the very first moment of time. We shouldn't have the reliable, logical progression of history, yet the math of the beginning provided the initial winding of the cosmic clock. Tonight, as you feel the slow, steady progression of time carrying you towards sleep, let the magnitude of this initial order settle over you. The math says you are an impossible island of complexity in a universe that should have been a mess. The math says your very ability to remember the past and anticipate the future is a result of a 1 in 10 to the power of 10 to the 123 chance. But the reality is that you are here, breathing and thinking, in a world of structure and beauty. You are the beneficiary of a mathematical order that defies all reason. Sleep now, and let the cosmic clock continue its long, improbable tick. You are the universe's most ordered and beautiful exception. The quiet of the late hour brings us to the math of the weak nuclear force and the mass of the W and Z bosons. To understand why the equations say we shouldn't be alive, we must look at the messengers of the force that allows for radioactive decay and the very first step of nuclear fusion in the Sun. In the standard model of particle physics, the weak force is carried by particles called the W and Z bosons. The math says that these particles are incredibly heavy, nearly 100 times the mass of a proton. This heavy mass is what makes the weak force weak and short-ranged. If the math of the Higgs mechanism, the process that gives these particles their weight, were slightly different, the entire cosmic story would be rewritten. If the W and Z bosons were significantly lighter, the weak force would be much stronger and act over longer distances. In the early universe, this would have caused protons to transform into neutrons far too efficiently. The math shows that we would have ended up with a universe made entirely of helium, with no hydrogen left to form water or long-lived stars. If the bosons were much heavier, the weak force would be so stunted that the Sun's nuclear fusion could never ignite. The math says we are living in a universe where the weight of these invisible messengers was set to a specific value that allows for a slow, steady sun and a chemically diverse cosmos. We shouldn't be here to feel the warmth of the day, because the math of the weak force says the Sun should have been either a bomb or a dud. As we continue our exploration of the impossible, we must confront the math of the Earth's atmosphere and the Rayleigh scattering. We take for granted that the sky is blue and that the air is transparent, but the math of how light interacts with gas molecules says this is a vital part of our survival. The Earth's atmosphere is a specific mix of 78% nitrogen and 21% oxygen. The math of this composition is what allows visible light from the Sun to reach the surface while blocking the most harmful high-energy radiation. If the density or the molecular makeup of our air were different, the math of optical depth shows we would be living in a world of permanent twilight or lethal radiation. If our atmosphere were much thicker, like that of Venus, the math of the greenhouse effect would be a death sentence. The Sun's heat would be trapped with such efficiency that the oceans would boil away, leaving a dry, pressurized hellscape where no complex chemistry could survive. If it were much thinner, like Mars, the math shows that the liquid water in our cells would evaporate into the vacuum. We are living in a mathematical pressure seal. The weight of the air above you, roughly 14.7 pounds on every square inch of your body, is perfectly tuned to keep your water liquid and your temperature stable. We shouldn't have a breathable world, yet the math of the Earth's gravity and volcanic history gave us this thin blue line. This leads us to the math of the oxygen window. Oxygen is a highly reactive gas. In high concentrations, it is actually toxic to life and makes the world incredibly flammable. If the math of our atmospheric oxygen were 25% instead of 21, the math of combustion probability says that forest fires would be started by the slightest spark and would be almost impossible to extinguish. The Earth's vegetation would be perpetually charring. If it were below 15%, the math of aerobic respiration shows that large, active animals like us could never get enough energy to move or think. We are living in a narrow chemical corridor. The math says we shouldn't be alive as active, air-breathing beings. According to the laws of planetary evolution, an atmosphere is usually a toxic mix of carbon dioxide or a thin veil of nothingness. Yet, we have a sky that is just right for both fire and breath. Tonight, as you take a deep, slow breath of the cool night air, let the specificity of this mixture settle over you. The math says your lungs should be either parched or burning, but the reality is that you are breathing a perfectly balanced cocktail of gases that has been maintained for millions of years. You are the beneficiary of a biological and geological handshake that keeps the air clear and the fires contained. Sleep now and let the atmosphere continue its protective, improbable embrace. You are the universe's most beautifully aerated miracle. The profound stillness of the night brings us to the math of the universe's initial expansion and the flatness problem. To understand why the equations say we shouldn't be alive, we must look at the starting speed of the cosmos. At the very first fraction of a second, the universe was expanding at a rate that is almost impossible to imagine. Opposing this expansion was the inward pull of gravity from every particle of matter. The math of general relativity tells us that for the universe to survive for billions of years, long enough for a single cell to evolve, the balance between this expansion and gravity had to be essentially perfect. This balance is often described by the density parameter, omega. If the density of the universe, at 1 nanosecond after the Big Bang, had differed from the critical density by as little as 1 part in 10 to the power of 24, the math says our story would have ended before it began. If the universe were slightly more dense, gravity would have slammed the brakes on the expansion, leading to a big crunch within a few million years. If it was slightly less dense, the universe would have flown apart so fast that matter could never have clumped together to form a single star. We shouldn't be here because the geometric shape of the universe is a mathematical tightrope walk that has lasted for 13,800,000,000 years. This leads us to the math of the inflationary epoch. Most cosmologists believe that to achieve this impossible flatness, the universe underwent a period of exponential expansion called inflation. In a tiny burst of time, space grew by a factor of 10 to the power of 26. The math of inflation is the only thing that explains why the universe is so smooth and so flat. But inflation itself requires its own set of finely tuned math. If the energy field that drove inflation, the inflaton, had been slightly stronger or lasted a fraction of a second longer, the universe would be far too empty for galaxies. If it had been weaker, inflation would have failed to smooth out the chaos. The math says we are living in a Goldilocks expansion that was corrected by a Goldilocks inflation. We shouldn't be here to measure the flatness, because the math says the universe should have been either a point or a mist. As we continue our exploration of the impossible, we must confront the math of the speed of light and the fine structure constant. The speed of light is roughly 300,000 kilometers per second. It is the universal speed limit, but it is also a fundamental constant that dictates how atoms hold together. The math says that the speed of light is inextricably linked to the strength of the electromagnetic force through a value called the fine structure constant, which is approximately 1/137. If this number were even slightly different, the math of chemistry would be rewritten in a way that excludes life. If the fine structure constant were just a few percent larger, the math of the atomic nucleus shows that the electrical repulsion between protons would become so strong that the strong nuclear force could no longer hold them together. All elements heavier than hydrogen would become unstable and fall apart. There would be no carbon for your cells and no oxygen for your breath. If it was slightly smaller, the electromagnetic force would be too weak to keep electrons in their orbits. Atoms would be loose and fragile, and the delicate chemical bonds that form DNA would be broken by the slightest warmth. The math says we should be living in a universe of dark, unstable gas. Instead, the speed of light and the strength of the atom are locked in a mathematical harmony that allows for both solid matter and the light we use to see it. This leads us to the math of the proton to electron mass ratio once again, but viewed through the lens of thermal stability. The fact that a proton is nearly 2,000 times heavier than an electron is what allows for the existence of solid objects. Because protons are heavy, they stay relatively still, while light electrons move around them to form bonds. If the masses were closer together, say, if the electron were much heavier, the math shows that the uncertainty of the proton's position would be so large that stable crystal structures and long molecular chains would be impossible. Your body would be a quantum blur rather than a solid entity. The math says we shouldn't be alive as complex, three-dimensional beings with reliable shapes. According to the laws of quantum mechanics, the masses of these particles should be random, yet they are set to a ratio that allows for the stiffness of matter and the precision of the genetic code. We shouldn't be able to rely on the physical integrity of our own bones, yet the math of the subatomic world provides the foundation. Tonight, as you feel the firm, solid support of your bed, remember that you are built on a mathematical ratio that keeps you from dissolving into a cloud of probability. You are the universe's most stable and beautiful structure. Sleep now, and let the atoms of your body continue their silent, improbable dance. The quiet of the late night often brings us to the edge of the math of the weak nuclear force and the sun's longevity. To understand why the equations of physics say we shouldn't be alive, we must look at the rate-limiting step of the nuclear fire that warms our world. The sun is powered by a process called the proton-proton chain, where hydrogen nuclei fuse into helium. But there is a mathematical bottleneck. The first step of this chain involves two protons fusing together, and one of those protons must simultaneously transform into a neutron via the weak nuclear force to create a deuteron. The math says that this event is incredibly rare. The probability of two protons successfully forming a deuteron during a collision is so low that a single proton in the sun's core will, on average, wait 9 billion years before it successfully undergoes this transformation. This slowness is the only reason the sun hasn't exploded like a colossal hydrogen bomb. The math of the weak nuclear force acts as a celestial thermostat, ensuring that the sun burns its fuel slowly and steadily over 10 billion years. This provides the stable, long-term energy source required for the slow, 4 billion year crawl of biological evolution on Earth. If the weak nuclear force were slightly stronger, the math shows that the fusion process would be far more efficient. The sun would burn through its entire supply of hydrogen in a few million years, exhausting its fuel before life even had a chance to move beyond single-celled organisms. If the force was slightly weaker, the fusion process would never ignite, and our sun would be a cold, dark sphere of gas. The math says we shouldn't have a stable, long-lived star to provide us with warmth. We are the beneficiaries of a force that is tuned to be just weak enough to prevent a catastrophe, but just strong enough to light the darkness. Tonight, as you feel the residual warmth of the day in your room, remember that you are being fueled by a nuclear reaction that the math says is a 9 billion year waiting game. As we continue our exploration of the impossible, we must confront the math of the Earth's core and the geodynamo. We live on a planet with a heart of liquid iron and nickel, and the math of this molten center is what keeps us safe from the radiation of the stars. As the Earth rotates, the churning of this liquid metal generates a massive magnetic field that extends far out into space. This magnetosphere acts as a shield, deflecting the solar wind, a stream of high-energy charged particles from the sun that would otherwise strip away our atmosphere and boil away our oceans. The math of the Earth's magnetic field is a delicate balance of temperature and pressure. For the geodynamo to function, the core must be hot enough to remain liquid, but cool enough to allow for convection currents. The math says that if the Earth was slightly smaller, its core would have cooled and solidified billions of years ago, much like Mars. Without a magnetic field, the solar wind would have scoured our planet clean of air and water, leaving us a dry, irradiated wasteland. If the Earth was slightly larger, the higher pressure might have prevented the inner core from solidifying at the right rate, potentially disrupting the magnetic field stability. This leads us to the math of the radioactive decay within the Earth. The heat that keeps our core liquid comes from the decay of radioactive isotopes like uranium and thorium. The math says that the abundance of these elements in our planet's crust and mantle is a fluke of our solar system's formation. If we had fewer radioactive elements, the Earth would be geologically dead, with no plate tectonics to recycle carbon and no magnetic field to protect our air. If we had too many, the Earth's surface would be a volcanic hellscape, too hot and unstable for life. The math says we shouldn't be alive on a geologically active, protected planet. According to the laws of planetary cooling, a planet of our size should be a quiet, cold rock by now. Yet, the math of our radioactive interior keeps the fire burning and the shield up. Tonight, as you lie in the stillness, remember that there is a spinning ocean of white-hot metal thousands of miles beneath you, generating an invisible force field that protects every breath you take. You are safe in the arms of a geophysical miracle. Sleep now, and let the Earth's core continue its silent, improbable work. You are exactly where you are meant to be, a beautiful truth that the numbers can only envy. The deep silence of the night brings us to the math of the strong nuclear force and the stability of the deuteron. To understand why the equations of physics say we shouldn't be alive, we must look at the very first step in the assembly of the universe's elements. In the beginning, there were only protons and neutrons. For anything more complex to exist, for the stars to shine, or for the carbon in your heart to form, these two particles had to join together to create a deuteron, the nucleus of heavy hydrogen. The math of this bond is the absolute threshold of existence. The strong nuclear force is what pulls these two particles together, but its strength is set to a value that is almost precisely at the minimum required level. If the strong force were just 5% weaker, the math shows that the deuteron would be unbound. It simply would not hold together. In such a universe, the chain of element building would be broken at the very first link. No helium could form, no stars could ignite, and the universe would remain a lonely, cold expanse of simple hydrogen gas forever. The math says we are alive because the glue of the universe is just barely strong enough to keep the first brick of reality in place. On the other hand, if the strong force were just 2% stronger, the math of the early universe would have been equally terminal. In that scenario, two protons would be able to bind together to form a diproton. This would have caused the Big Bang to be far too efficient at fusion. Instead of leaving behind a universe full of hydrogen for water and long-lived stars, every single proton would have been consumed and turned into helium within the first few minutes of time. The math says we shouldn't be here because the fuel of life should have been used up in a flash of cosmic fire. We are the survivors of a mathematical balance that is tuned to allow for a slow, complex future. As we continue our exploration of the impossible, we must confront the math of the Earth's albedo and the greenhouse effect. We live on a planet that maintains a remarkably steady temperature, but the math of climate is a chaotic dance of reflection and absorption. The Earth's albedo is the percentage of sunlight that is reflected back into space by clouds, ice and sand. The math says that if the Earth were just a bit more reflective, if we had slightly more cloud cover or larger ice caps, we would enter an irreversible icehouse state, where the planet would freeze solid from pole to pole. Conversely, if the Earth absorbed just a few percent more of the Sun's energy, the math of the greenhouse effect says we would suffer a runaway heating. As the temperature rises, the atmosphere can hold more water vapor, which is itself a powerful greenhouse gas. This creates a feedback loop that could turn the Earth into a sister planet to Venus, with surface temperatures hot enough to melt lead. The math says we shouldn't be living on a temperate liquid water world. According to the laws of atmospheric physics, our climate should be an unstable pendulum, swinging between fire and ice. This leads us to the math of the carbon cycle and plate tectonics. The Earth has a natural thermostat that regulates its temperature over millions of years. Carbon dioxide is washed out of the air by rain and eventually buried in the seafloor. Plate tectonics then carries this carbon deep into the Earth, where it is eventually released back into the atmosphere through volcanic eruptions. The math of this cycle is what has kept the Earth from freezing or boiling for 4 billion years. If the rate of subduction were slightly slower, or the volcanoes slightly more active, the math shows our atmosphere would have long ago become toxic or vanished. The math says we shouldn't be alive on a planet with such a reliable thermostat. Most planets are either stagnant rocks or volcanic hellscapes. Yet, the math of the Earth's interior and its surface water works in a perfect, accidental harmony to keep the temperature just right for life. Tonight, as you feel the cool night air and the warmth of your own breath, remember that you are the beneficiary of a planetary balancing act that has never failed. You are safe in the arms of a geochemical miracle. Sleep now and let the Earth continue its silent, improbable regulation. You are the universe's most beautifully stabilized result. The profound stillness of the night brings us to the math of the proton-to-neutron mass ratio once more, but this time through the lens of the hydrogen window. To understand why the equations of physics say we shouldn't be alive, we must look at the tiny difference in weight between the two main inhabitants of the atomic nucleus. A neutron is slightly heavier than a proton by about 1/10%. This sounds like a negligible rounding error, but the math says it is the fundamental reason the universe is not a graveyard of dark neutral particles. Because the neutron is slightly heavier, it is inherently unstable when left alone. A free neutron will decay into a proton in about 10 minutes. This ensures that the early universe was filled with hydrogen, the simplest atom consisting of a single proton. If the math were reversed and the proton were the heavier particle, every proton in the cosmos would have decayed into a neutron shortly after the Big Bang. In a universe of pure neutrons, there would be no electric charge, no atoms, no chemistry, and no light. The math says we are living in a reality that was saved by a fraction of a percent in mass. Furthermore, the math of this mass difference is what allows for nuclear stability in heavier elements. When a neutron is tucked inside a nucleus with protons, the binding energy actually reduces its effective mass, making it stable. If the mass difference were just a tiny bit larger, neutrons would decay even inside the nucleus, causing all the atoms of your body to turn into hydrogen and explode in a burst of radiation. If the difference was smaller, all the hydrogen in the universe would have fused into helium in the first few minutes of time. The math says we are living in a sweet spot of mass. We shouldn't have the electrical charge required for life, yet the math of the neutron's weight gives us the power to be. As we continue our exploration of the impossible, we must confront the math of the triple alpha bottleneck from a different angle. We have discussed how carbon is made, but the math of its survival is just as improbable. Once carbon is forged in a star, it is very easy for it to capture another helium nucleus and turn into oxygen. If the energy levels of the oxygen atom were just slightly different, the math of nuclear physics shows that every single atom of carbon would be converted into oxygen almost instantly. The universe would be filled with water and rocks, but there would be no carbon left to build the long, complex chains of organic chemistry. The math of the oxygen nucleus is tuned to be just slightly off resonance, which acts as a mathematical brake, preventing the stars from consuming all the carbon they create. We shouldn't be alive in a universe that has both the breathing element and the building element. According to the laws of nuclear probability, we should have been a world of one or the other. Instead, we have the perfect mixture. This leads us to the math of the stellar habitable zone and the lifetime of our sun. The math of gravity and nuclear fusion says that the more massive a star is, the shorter its life. A star twice as big as our sun burns out in a few 100 million years, not nearly enough time for complex life to evolve. A star much smaller would be so dim that a planet would have to orbit so close it would become tidally locked, with one side always scorching and the other always frozen. The math says our sun is in a rare mass window that allows for both longevity and a wide, stable, habitable zone. The math says we shouldn't be alive on a planet with such a long, steady supply of energy. Most stars in the galaxy are small, violent red dwarfs that would fry a planet with radiation or leave it in the dark. Yet, the math of our sun's specific mass gave us 4 billion years of quiet stability. Tonight, as you feel the steady, rhythmic breathing of your own body, remember that you are the result of a nuclear break and a stellar window. You are made of carbon that the stars refuse to turn into oxygen, living on a planet that the sun refused to burn. You are the universe's most beautifully spared result. Sleep now, and let the stars continue their silent, improbable forge. You are safe in the arms of a miracle. The quiet of the late hour brings us to the math of the universe's fine structure constant and its role in the very nature of light. To understand why the equations say we shouldn't be alive, we must look at the number that determines how strongly light interacts with matter. This value, approximately 1 over 137, is a pure number with no units, yet it dictates the entire visual and chemical world. The math says that if this constant were even slightly different, the universe would be a dark, incoherent place where the very concept of sight or solid matter would be impossible. If the fine structure constant were just a few percent larger, the math of the atom would change in a way that would make life stop before it started. A stronger electromagnetic force would mean that protons in the nucleus would repel each other with such violence that the strong nuclear force wouldn't be able to hold them together. All elements heavier than hydrogen would become unstable and fall apart. There would be no oxygen to breathe and no carbon to build a body. Furthermore, a larger constant would make stars much more opaque, causing them to swell and cool until they could no longer support the nuclear fusion that creates life's ingredients. The math says the universe would be a graveyard of unstable atoms and bloated, dying stars. On the other hand, if this constant was slightly smaller, the math shows that the electromagnetic force would be too weak to keep electrons in their orbits. Atoms would be loose and fragile. Chemical bonds, which are the basis of all biology, would be so weak that they would break at the slightest hint of heat. Molecules like DNA, which require a precise and steady electrical grip to maintain their double helix shape, would unravel into a useless tangle of atoms. The math says the universe would be a place of supreme simplicity, a collection of cold, drifting particles that never learned how to join together to form a complex thought. We are the beneficiaries of a number that is so perfectly tuned that it allows for the existence of both solid objects and the light we use to see them. This leads us to the math of the stellar window. The light that comes from our sun is almost entirely in the visible spectrum, the narrow band of colours that our eyes can see. The math of physics says that this is not a coincidence. This specific range of light is the only part of the electromagnetic spectrum that can trigger chemical reactions, like photosynthesis, without being so energetic that it destroys the molecules it hits. If the sun's light were shifted toward the ultraviolet or the infrared, the math of biology says that life as we know it could never have begun. We shouldn't be here to see the light, because the light shouldn't have been just right for our chemistry. Yet the math of the sun's temperature and the math of our molecular bonds are in perfect, improbable alignment. We have reached the end of our journey through the impossible. We have looked at the math of the Big Bang, the math of the stars, and the math of the atoms in your own body. At every turn, the equations have said the same thing. You shouldn't be here. The probability of the universe starting with such low entropy, of gravity being so weak, of carbon having such a precise resonance, and of the Earth being so perfectly protected is essentially zero. If you were to multiply all these coincidences together, you would arrive at a number so small that it suggests we are the most improbable event in the history of existence. But the math also tells us something else. It tells us that we are not an accident, but a consequence. The very fact that you are here, reading these words and reflecting on these numbers, is the ultimate rebuttal to the logic of chance. The math says we shouldn't be alive, but the reality is that we are the way the universe has found to witness its own beauty. We are the observers that the laws of physics seem to have been waiting for. Perhaps the math isn't telling us that we are a mistake. Perhaps it is telling us that our current understanding of the equations is missing a deeper, more elegant truth that makes life inevitable. As you settle into the final, deepest layer of sleep, let the weight of these 40 sections rest gently on your mind. You are the survivor of a 13 billion year series of miracles. You are protected by a magnetic field generated by a molten core, warmed by a star that burns with a controlled nuclear fire, and built of atoms that were forged in the hearts of giants. The math of the universe is a cold, silent language, but your life is the poetry that it writes. You are the rare, beautiful exception that proves the rule of existence. The numbers are done now. The equations are silent. The universe is watching over you with a precision that defies all calculation. You don't need to solve for X to know that you are loved by the laws of physics. You are exactly where you belong, in a home that was prepared for you since the first second of time. Sleep now, in the quiet certainty of your own existence. You have already won the greatest lottery in the history of the cosmos. The math says you are impossible, but your heart knows the truth. You are the most beautiful truth the universe ever calculated. Good night, and sleep well in the arms of the miracle.